Hello and welcome to our as yet unnamed podcast. Today we will be doing mathematical induction.
And we're gonna mainly focus on in the manual that's page 49 to 50. And hopefully this might be helpful for those of you who might still be confused.
Basically, the essential principle of mathematical induction, by title, is to say that if you have two things are equal, and then you add something to both sides.
Same thing, let's just say.
If you can show that it will still be equal after doing that, and that it will be equal no matter how much you add to both sides, you can. The mathematical induction is sort of the argument that it will be equal to infinity.
So the equality will hold like for any case.
And then even if you had infinite sums on both sides, the equality would still remain because you added it one finite amount at a time, and you know that each time you add it, it will remain equal. So, before we get into the nuts and bolts of mathematical induction, we thought we would briefly go over the sigma notation and how that works. To start off with,
this is on page 50.
Right. Yeah. To start off with, we've got a sigma in the middle.
Big sigma.
Which stands for sum. And beneath it, we're going to have j equaling usually 1. Sometimes it could equal something else. And what all that is saying is that the first term, this is defining the first term of the sequence of numbers that you're going to be adding up.
So this is kind of like an iterator for the sequence.
Yeah. It's like where you're starting off. And then at the top, we're often just going to have an n. And that n stands for the last term, sort of the last j of your sequence.
The last term.
And then to the right of the sigma, we'll have the operation that you're doing to each of the terms 1, 2, 3, 4, 5, etc. In this case, let's do j squared.
J squared. So this is gonna be this thing on the right side of the sigma notation is gonna be the rule for every term in the sequence.
Yeah, and also if you're looking at the manual, this is what number d looks like, but we're not going to be going through all of it. This is just the rule that was in that case. So all that this is the same thing as saying 1 squared plus 2 squared plus 3 squared plus 4 squared and so on until you reach n, whatever that is.
N squared, right?
Yes. So if you knew what n was, if for instance n was 6, it would just be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, and that would be precisely equal to what we have here, this entire sigma phrase.
So just like Mr. Barry said, if we make it specific and say that if n is equal to 6, and then we just write down the sigma notation where j starts with 1, right? And we keep the rule j squared. So this whole thing is going to be representing the sum of the sequences starting from 1 squared to 2 squared to 3 squared plus 4 squared plus 5 squared plus 6 squared. So these two things are going to be equivalent.
Right. And so what we're doing here when we have a sum of a sequence, when you leave it in terms of n, you're keeping this more general, but you're really still doing this same process down here. You're just leaving it, that ellipsis there is standing for terms, you don't know how many of them there are, but it's still the exact same thing.
Right.
So then to use another example, suppose we had the rule, still page 50, part B. Suppose we had the rule j times j plus 1. So you're still going to have the sigma. J still equals 1 to start with. J times j plus 1. And let's just say, so you have n there. In the same case, this equals precisely 1 times 1 plus 1.
1 times 1 plus 1. That's going to be the first term.
Right. Plus 2 times 2 plus 2.
2 plus 1.
Sorry,
right.
1.
Mm-hmm.
And so in each case, the j is being replaced by the next term.
Uh-huh.
So then 3 times 3 plus 3.
3 plus 1.
Whatever.
Wait, it's 3 plus 1, right?
It is, yes.
Go on to infinity until you reach the last term where it's in.
Yeah.
And then you just substitute in with j so that you get last term would be n times n plus 1.
Yeah. So again, if you had, in this case, you could have n being a finite number, and in that case you would be able to figure out precisely what this sum is simply by adding them all up.
Mm-hmm.
If it were 5, it would just be 1 times 1 plus 1 plus 2 times 2 plus 1,
Right.
then 3 times 3 plus 1 plus 4 times 4 plus 1 plus 5 times 5 plus 1.
Okay, I'm not going to write that, but
okay,
you get it.
And that would be it. That sum would be the precise amount that this notation on the left here equals.
Mm-hmm. But so far we only talked about the left side of the equality.
Right.
And then this is only going to be part of the thing that we're trying to prove for mathematical induction.
Mm-hmm.
And now we jump right into the right part of the equality.
Right.
So if we still stick with this example that is exercise B on page 50, we'll see that on the right side, this whole summation is going to be equal to the right side. That is, what is it? N times
n plus 1 plus times n plus 2 over 3.
Over 3. So we know that this notation, the sigma notation, is equal to the sum of a sequence that's on the right side. And we know that this notation is also going to be equal to this notation, n times n plus 1 times n plus 2 over 3. So consequently, we know that these two are also equivalent. Mm-hmm. So that means the sum of the sequence over here on the right side can be calculated by the formula on the right side. And in our case, it's on the bottom. That is n times n plus 1 times n plus 2 over 3.
Right. And that's what most of these problems are aiming to prove, that this one algebraic formula here, like we have here, n times n plus 1 times n plus 2 over 3, that one thing will be true no matter what your n is. So it would be true if n were 5, or if it were 100, or if it were infinitely large.
Mm-hmm.
And since it's not, when you have this, what we have here in the upper right, and this underline there, that never ends. There's no finite ending point to that. It could, in theory, go on, that ellipsis there implies that it could go on infinitely if your n were large enough. However, the formula that we have on the bottom here is never going to change. It's going to remain this fairly small,
mm-hmm.
It's a little complicated, but mm-hmm. fairly small formula forever, which is why it's useful.
Right.
And that's sort of what we're doing here, is trying to find this finite summation of an infinite series.
Right. So why don't we just jump into exercise A and then C and then just finish the whole proof?
Yeah.
Okay. Just gonna move this to a side.
There we go.
And now we're on still page 50,
exercise
A. We're trying to prove that the left side, that is j equals to 1, the rule for each term is j. It's going to be equal to this formula.
Mm-hmm.
That is n times n plus 1 over 2.
And to maybe state this in a little bit more plain English, what all that the rule here being j means is that this is going to be the sum of natural numbers. So 1 plus 2 plus 3 plus 4 plus 5. What we're going to do is we're going to do the two-step thing. So first, we just simply need to prove that this is true in one case.
This is in reference to page 49.
It's all boldy and it says the first step.
Yes, the first step.
Very dramatic. So let's just say n is 2, because that'll make things very
So what are we trying to do in the first step?
Oh,
we want
so,
to verify...
Yeah. What? We're verifying that this is an equality in at least one case, or in just one case.
In one, like, one particular case?
Yeah, exactly. So for n being one particular value, that is, when n is a particular value, we have one series. So if n is 2, this is just 1 and 2 are the only two numbers that we're going to use, that we're going to sum together.
So let's say when n equals to 2,
yeah,
and then we'll just substitute everything?
Yeah, so on the left, since we know that the sigma notation on the left is the same as just adding the sum, we'll say, well, the first j is 1, so we'll just take that.
1.
And there's nothing we have to do to it because the rule is just j. And then we'll add the second number in the series, which is 2. And that's where we end, because n being equaling 2 means that 2 is where you stop.
It's the last term.
Yeah.
And then last term, we know the last term from the rule j over here. So we'll have 1 plus 2, that's going to be equal to 3.
Oh, cool.
This is what we get from the left side.
And then we can take the n, then n is still being 2, and we'll plug it into the right side in that equation right there. So we'll have 2 times 2 plus 1 over 2. And if you multiply that out, that's 2 times 3 over 2. That's 6 over 2, which is 3. Oh, okay. So that means that
that thing is going to equal to this 3.
Exactly. So for at least one instance, for the instance of n equaling 2, the algebraic sum on the right half here does actually summarize the sequence on the left.
So we know that this equality holds when n equals to 2.
Yeah.
And that is one particular case.
Right.
And we finish. So after we're doing that, we verify that both sides are gonna have the same value. Then we just finish the first step. Right?
So then, what the second step is going to do for us is it's going to say that, well, we now we're going to assume that it works in one case, but we know that it works in one case. What we're going to say is, no matter what case we have, we're going to show that for the next case, it will also be true that this will remain equal. Or you could say that the algebraic thing on the right will correctly summarize the sum on the left. And so if that's true for every single case, we already know that it's true for the case of 2. And then we could apply and say, oh, well, it's true for the case of 3, because we know it would be true for the next case. But then we could take 3 as our assumption and say, oh, well, then it's true for the case of 4. And then, oh, it's true for the case of 5. It's true for the case of 6, and so on, for every number to infinity.
Right.
Which is why this step 2 is going to be phrased in terms of n, so that it works no matter what your n is. You'll know that the next number, the next n, will always hold. Right. And thus, what we're putting forward is that since every single number it holds for, it will hold... No, sorry, if it holds for any single set where from one number to the next, it will hold for every set on to infinity.
And in order to avoid being confused with n as being the last term in the previous summation, we just, instead of using n, we use k. Right? That's all.
Are we going to do that?
Are we going to use k or n?
I was just going to use n.
Okay, we just use it. But keep in mind that this n that we're going to use in step 2 is going to be different than the n that's here.
And yeah, because our ceiling, sort of, our last term is becoming 1 higher. That's sort of, instead of being 1 plus 2, it could be 1 plus 2 plus 3, or it could be 1 plus 2 plus 3 plus 4. In each case, that limiting thing, the limitation of n, is becoming 1 greater. Right.
So, just like Mr. Berry said, if we just suppose that, so I'm going to write a if this summation j equals to 1, where you have the rule j, the last term is n, is equal to n times n plus 1 over 2. So we assume that this equality holds. Just put a check over here. And then we have to prove that, what are we trying to prove?
We're trying to prove that if you put n plus 1 in the place of each n, if you increase n by 1, the equality will still hold.
That means we add both sides on the same thing.
Well, I mean, you're adding in the sum. So in the left half, it is a sequence of additions. So you're just adding one more term.
So the new last term would be n plus 1.
Instead of like we have up here, so you have like 1 plus 2 plus 3 plus 4 plus 5 ellipsis plus n. Now we're going to say, oh, it'll be plus n and then plus n plus 1.
Alright, I'm going to use a different color.
Yeah.
So this is going to be the next term that's after n.
Right.
This whole thing.
So that's all we need to do to the left side. That's making the sum 1 greater. And we can even write that by rewriting the sigma down there with just the sigma with n over it. And then plus n plus 1. That's all we're doing to the left half. But for the right half, we're going to substitute n plus 1 in the place of all of the n's. Because n plus 1 is our new limit. It's our new highest term in the sequence. So since on the right half, n is simply standing for the highest term, we need to change that, or else that would be, this is a more accurate way. Since n plus 1 is our new n, basically. Maybe that's the best way of saying it.
Yeah, so we just substitute n plus 1 with n.
Yeah.
So you see on the original equation we have n for the first term. So we just substitute that with n plus 1 over here. And then this n also going to be substituted by n plus 1 over here. So it's basically the same thing. All we did was add 1 to n and then substitute the whole thing with the original n, and then keep the rest are the same.
So if our original equation, n times n plus 1 over 2, if that's an actual valid rule, doing this to both sides should maintain the equality. We know it's equal in the first case, but if we can prove that it's equal in the second case, we know that it will work. That will set up our chain of dominoes and say that it works in every case.
Right. So we don't know yet if these two are equal.
Question mark? Yeah, exactly. That's what we're trying to prove. Yep. We're hoping it's true. And to do that, at least the way I found most natural, is to work on the left side. We already know that n over the sigma over the j equals 1j, that part. Did you circle that?
Yep.
That part there, we know that that equals n times n plus 1 over 2.
That's the thing we assume. Right.
And so we can just say that plus n plus 1 is the same thing. That there is the same as the sigma notation times n plus 1.
Yep. So that's going to be equal to the sigma n plus 1. J equals to 1. J.
Right. What Mr. Wong just wrote there is another way, that right there is another way of saying that. Because n plus 1 being the new top term, it's the same as what Mr. Wong wrote up here. 1 plus 2 plus 3 plus 4 plus 5 plus n plus 1. Yeah, that part there. So that's another way of saying it.
Yep. So what we assume, I'm going to write it here, we assume is that j is equal to 1, and then we have the rule j is going to be equal to the formula n times n plus 1 over 2. We assume that's the case. If that's the case, then what necessarily follows is that if we add the same thing on both sides, and the equality still hold. Right? So in this case, we're just going to add the two things on the same side. And the thing we want to add to, in this case, is n plus 1.
Right.
So we just add n plus 1 on the left side and n plus 1 on the right side. So we know that if these two terms are true, if we add the same thing, n plus 1 on the left side, n plus 1 on the right side, the equality still holds.
Right. Right. That's a good way of putting it.
And then in that way, the left side, the whole of the left side, that is n plus 1 plus the sigma notation, is gonna be equal to this thing.
Mm-hmm.
That is, instead of having n as the last term, you have n plus 1 as the last term.
Mm-hmm.
And then the right side will be equal to this thing.
Mm-hmm.
And so what's left for us is trying to prove that this thing, whether this thing is going to be equal to n plus 1 times n plus 1 plus 1 over 2.
Right.
That's our goal. That's our job.
And that is actually, only, in this case, is only going to take a couple of algebraic steps.
Yes.
Because maybe you want to like just scroll it up a little bit so we can see the bottom.
Like that?
A little bit, right. Yeah, like that. Okay. So we could also phrase what we have, cool new color, as n times n plus 1 over 2, right?
Yeah. N times n plus 1 over 2.
Yeah, and then plus 2 times n plus 1. It's 2 times and then in parentheses, yeah. Over 2. That, what we have after the plus there, is the same as just n plus 1, because it's multiplied by 2 and divided by 2.
Mm-hmm.
And we're just doing this, yeah.
So that becomes this whole thing.
Exactly. And we're just doing that so that we can have 2 as the denominator in both cases.
So
and
that
then
we can simplify by having 2 on both sides.
And then we can just say n times n plus 1 plus 2 times n plus 1. And then, is this called the distributive property?
I think it's called like factoring.
I guess, I mean...
Or just, basically what you do is that you see on the left side of the term you have n plus 1, right?
Right.
And you also see that in the right side.
So it's multiplying both n and plus 2?
Yeah, so it's like you take the common term n plus 1 on both sides. You just take it and then write it out and then add the rest together?
Yeah, and you can say since it's multiplying n and it's also multiplying 2, you could just say it's multiplying n plus 2.
Over 2.
Which is what we had up here, right? Yeah, that. So it's no longer a question whether or not they equal each other.
Which is also that thing.
Right.
Which is this thing.
Right.
And we are done.
Woo. Because we have shown that this equality maintains if you add n plus 1 to both sides. So we know it was true in one case where n equaled 2. Then we can say, oh, well, it's true for the next case when n equals 3. Oh, it's true for the next case when n equals 4. It's true for the next case when n equals 5. It's true for every single case out to infinity. So no matter what n is, or even if n is infinitely large, or even if n is just the sum of all natural numbers, we know that it will equal, what, infinity times infinity plus 1 over 2?
But please do keep in mind that this is only the case for proving equality where you have sequences on the left side that's going to be equal to a formula on the right side. But you can also have different kinds of like inductions. For example, like in exercise 2 on page 50, instead of having equality, you have inequality. And instead of have sum of the sequences, you have a multiplication that's happening on both sides. So the main method is gonna stay the same, but the particular cases for solving different kinds of inductions are gonna be different.
Yeah. Cool.
Yeah, I think that's it. It's 11:30. We're going for lunch. Hope you guys have a good long weekend.
Yeah, join us for our next podcast, which will be at some indeterminate time in the future.
Yes. All right, that's it. Thanks, guys.
Yep.
See you next time.